Welcome back to ICSE Physics Class 10. We're in Chapter 1 called Force, and in this video we'll be dealing with Part C, which is Uniform Circular Motion. We'll be starting off this video by tackling what exactly uniform circular motion is, and then we will also deal with what is the necessary force to create uniform circular motion, which is the centripetal force. Later, we'll be talking about a fictitious force called the centrifugal force, which helps us explain uniform circular motion while we are in a reference frame that doesn't necessarily notice the uniform circular motion. To start off, let's find out what is uniform circular motion. So, circular motion is whenever any object is following a circular path. The term uniform comes when we say that it's covering equal distances along the path as it moves in equal intervals of time. Which means if we assume that it takes about 1 second for the object to go from this point to this point, that means this arc takes 1 second. That means that in the next 1 second, it should cover from here to here. In the following 1 second, it will cover this distance. And finally, in another second, it'll cover this much. So that is what creates uniform circular motion. In case of linear motion, we have an object moving along a straight line, and in equal intervals of time, let's say 1 second it covers this distance, in the next second it'll cover exactly the same distance again, and in the final second it'll cover the same distance once again. So this would be uniform linear motion. In case of uniform linear motion, we can see that the direction of movement is always in the same direction. And if the direction of motion is the same, we can state that the velocity is constant because we're moving equal distances in equal intervals of time and the direction is the same. But in case of uniform circular motion, clearly we can't specify a direction. What the direction of motion is, we will look at in a second, but even without knowing the official direction of motion, you should be able to notice that we can't fix a specific direction. We can't state north, south, east, or west because it keeps changing the direction in which it's moving. And therefore, the velocity cannot be a constant because velocity is a vector and vectors have to have direction. And if we cannot specify a direction, that means the velocity is changing. And if the velocity is changing, we can state that it is accelerating. Now, what type of acceleration is occurring will actually be studied in future classes. There are two types, which is centripetal acceleration and tangential acceleration. However, that's out of the scope of syllabus, and this is all you need to know. But let's take a look at what is the direction of velocity in case of this rotating body. So let's take a closer look at the path. If we see a circular path, and we zoom in, just as we've done in the previous classes, we can actually notice that the path is made up of very small straight lines. So if we were to take a singular straight line and then extend it, we'd see that this should be the direction of motion for that particular interval. So if we zoom out, we realize that that direction seems to be like a tangent to the circle. So remember, a tangent is a line that touches only one point of the circumference. Properties of tangents will be studied in your mathematics classes, where you realize that it's always perpendicular to the radius of the circle. So now that we know that the direction is actually tangential, we can see that if we keep reducing the sizes of these straight lines, eventually once they become a point, the direction should still remain tangential. And therefore, the direction at this specific point is going to be in this direction. Whereas at this point of rotation, the direction will be like this. And the same can be said for every single point along the circumference. So therefore, we know that the direction of motion in uniform circular motion is always tangential to the circular path of motion. So now that we can see how the motion actually is, we can clearly see that the direction of motion is changing at every single point. And in order for a change to occur, there has to be some sort of force, because when there's an acceleration, there must be a force. So what direction should this force be acting? So if we take a look at this, if the velocity continued, it would have moved in this particular direction. But the original path curved away like this. So therefore, there is a small distance created over here between the path that it would have taken and the new path that it took due to some sort of force. So in order for this type of a motion to occur, clearly the force should have been acting downward. So in this particular situation, the force would have been in this direction. So in this situation, clearly there is a distance formed, and therefore at this point, the force should have been like this. And therefore, we can actually see that the force is always acting towards the center. And that is where we come to our next portion of the chapter, which is the centripetal force. So the centripetal force literally means center seeking force. So this is a force that's always pointed towards the center. So if we take a look at it, it would look something like this. If there was a boy standing over here and he's whirling maybe a ball with a string, this black arrow pointing towards the center would be the tension in the string that's causing the ball to continuously change directions and actually move towards the center, and that is called centripetal force. Now remember that the direction of force is always towards the center, and the motion also seems to be towards the center, as we could see over here where the motion is always changing towards the center. But the distance between the object and the center does not change. So this would be the radius of curvature, and that would not change. But it still is always moving towards the center in a way. So another example of centripetal force that's given in your textbook is the nucleus of an atom and the electrons. The positively charged nucleus remains in the center, and you have negatively charged electrons that rotate or orbit around the nucleus in a somewhat circular path. And they state that this is happening due to the electrostatic force of attraction between the two, which acts as the centripetal force. However, personally, this would be a bad example for centripetal force because these objects are actually quantum objects. And for quantum objects, you require quantum mechanics. And the position of the electron is actually determined by the Schrödinger wave equation, which is denoted by the Greek letter psi, and is completely out of your syllabus. But it's fun to note that the wave equation and quantum mechanics is what determines the motion of electrons around the nucleus and not actually centripetal force. However, in case of the simplified model of the atom, which we now know is incorrect, the centripetal force can be used to explain that simplified model. However, since it's in your exams or in your syllabus, it's noteworthy that the simplified version can be used as an example of centripetal force. Another example which makes far more sense is the motion of planets around their host star. So there, the force of attraction occurs due to the gravitational force of attraction, which is always acting towards the center of the two bodies. And that is why planets are able to orbit around stars. Similarly, instead of just planets around stars, we could also have moons about planets as well. You should note that in all of these examples, there are forces acting, but the speeds remain the same. And because of that, they remain in equilibrium. And in this case, it would be dynamic equilibrium. So any example of uniform circular motion would be examples of dynamic equilibrium or equilibria. Before we move on, another thing that's necessary to note is that the direction of force is always changing. As you can see over here, because the direction of force is changing at any point of time, the acceleration is also variable. So therefore, both the velocity is changing and therefore it's accelerating, and the acceleration is also variable because the direction of force is also changing, and hence the direction of acceleration is also changing. So now let's move on to the last part of this chapter, which is the centrifugal force. So the centrifugal force is a fictitious force. Fictitious, which means fake. So centrifugal force is a fake force that we have to use in order to explain uniform circular motion for someone who cannot necessarily understand that there is circular motion occurring. So let's take an example. So let's look at this particular surface, which is rotating. The surface has a camera which will allow us to look at the surface and see what somebody standing on the surface, rotating with the surface, would be seeing. Okay, now let's assume that we take a ball and then quickly tie it to the center. We will see that this ball is going to be tied and the string is going to be taut, or it's going to be under tension. That means the string is basically going to be pulled. Now we all know that the string is being pulled because the ball wants to continue its motion in the same direction. See, like right here, it wants to move in this particular direction. However, since the string would have to physically extend to a longer distance, clearly you can see this distance is much longer than this one, the string cannot do that because it's already in tension. And therefore, the ball itself has to rotate and move in this circular path. And clearly, because the string wants to expand at any point of time, we see that that is the reason that the string is in tension. Hopefully it was clear that you can see that the string would have to stretch even more in order for the ball to continue its path in the linear motion. Remember that the ball would want to continue its path in the linear motion due to Newton's first law of motion, which is a body in motion remains in motion unless there's an external force acting on it. And since the motion is in this direction, it would want to continue in this particular direction. And that's why the string becomes tight. However, let's take a look at this from the perspective of an observer. So here, this man or woman who's standing over here would see that the ball is not moving. It remains stationary with respect to this platform. Now, I've added a few objects in the world so that we can actually notice that, yes, we are rotating. But let's assume that this is so large that the person cannot tell that he is actually rotating. So to him, he sees that the ball is stationary, but the string is tight. For the string to be tight or under tension, there must be some forces. He sees that the ball is getting pulled in by the tight string. So that means the ball is facing a force towards him or her. But since the ball is not moving, that must mean that the ball is in equilibrium and there must be an equivalent opposite force. So therefore, there must be a force pointed in the outward direction. And this is what we call centrifugal force because it explains why the string is tight and it also explains why the ball is not moving. But clearly, as we all know, there actually isn't any force that's pushing the ball outward or at least radially outward. But to somebody standing on the platform, he does see that there must be a force radially outward for this to work. Another concept that we should have spoken about is that most people think that this centrifugal force is the reaction force from Newton's third law of motion. However, for anybody who would be thinking that, this would be absolutely incorrect, and no one should make that misconception. The reason for that is that for Newton's third law of motion, both the forces firstly have to be real forces. And as we all know, centrifugal force is a fictitious force, and therefore it is not the reaction force. Another very important point to note is that the third law of motion, the action and reaction pairs cannot act on the same body. But here, both the centripetal force acts on the ball as well as the centrifugal force acts on the same ball. And therefore, it is not the reaction-action pair that's spoken about in the third law of motion. So in case there's a question that asks if the centrifugal force is present due to the third law of motion, which demands for reaction force for any action force, you have to note that no, the centrifugal force is not related to the third law of motion in any way. Hopefully that clears out a few misconceptions that you might have had. Now let's take a look at what would happen if at a certain point in time, this string happens to break. If the string was to break at, let's say, this specific position, we know that this ball would continue its path in the tangential direction. So that means it would continue its path in this specific direction. So let's say that it continues like this. So these are different instances in time. Now remember that the observer is still rotating. So he would see the balls in the positions as such. And let's take a look at it from the perspective of the observer. So the ball gets cut right here. As he moves, so this particular ball, this ball is where it should be, and this ball is where he sees the ball to be. So clearly the ball has moved a bit away from him. As he continues his motion, he sees that the ball is now this much further away from where it should have been. And then as he moves forward some more, he sees that the ball is now much further away. So similarly, if he continues moving, he would see the ball move even further away. But as you see, the ball is still moving in a straight path away from him. So hopefully you can see that the observer sees the ball is moving radially away from him. And that is why he can say that there must be a force acting in this specific direction. And that's why he states that the centrifugal force must be true. And in fact, as you can see, the ball is actually accelerating away from him. In the first section of, let's see how many frames are moving. So 1, 2, 3, 4, 5, 6, 7. About 7 frames, it moved only this much. Then 1, 2, 3, 4, 5, 6, 7. It moved a lot more. In the next 7 frames, it moves much more. And again, in 7 frames, it moves a lot more than that. So clearly the motion is accelerating, and that's why there must be a force, and that's why he calls centrifugal force to be present. However, we know that in originality, the ball is simply moving in a straight line, which is the same direction it would have been moving had there not been a string attaching it to the center, preventing it from moving in this particular path. So hopefully that made sense of why centrifugal force is considered as a fictitious fake force, because it clearly doesn't exist. It's just that the ball is moving in the same straight path, but the observer sees it moving away from him. Hence, there must be a force acting in that direction to that observer. So it's all about how you choose to view this particular scenario. So with that, we actually come to an end to this particular chapter, which was uniform circular motion, which is the last part of the chapter 1, which is force. As usual, if you have any queries, any doubts, leave them in the comment section and we will make an entire doubts video for this chapter, which will be present on Dayan Academy. Since this particular portion of the chapter does not have any numericals or derivations or formulae, we will not be having a specific video for this particular part of the chapter on Dayan Academy. However, Dayan Academy will have a video that deals with all of the doubts related to this entire chapter. So be sure to ask your questions in the comments as soon as possible so that we can address your doubts before your exams so that you can score a centum in physics. Be sure to check out the entire playlist, and till then, all the best for your exams.